Once again, welcome to the afternoon session. Today we have our resource person, Dr. Kamal Das sir. Just I'm going to brief about the Kamal Das sir profile. Dr. Kamal Das sir working as a research scientist in IBM Research since 2013. He holds masters in mathematics and PhD in computer science geosciences from IIT Kharagpur. His research interest and activity mostly on development and implementation of grid-based numerical models, HPC, AI in geoscience and alien domain. His past 5 years experience research interest explained it to AI application, ranging from agriculture to supply chain under the future climate. These are the a little brief about the our resource person. I think this session will be having great outcomes. You can get more knowledge in domain sector like practical way of knowledge. I would like to hand over the session to the Dr. Kamal Das sir. This now session is over to you, sir.
Thank you. Thanks a lot for nice introductions. Let me go to my screen, and then you can discuss from there.
Very good, sir. You can stop sharing the screen.
Yes, sir. Yes, sir. Done, sir.
Yeah, this is my first time I'm using Zoom. Maybe.
Yeah, there is something called share screen, sir. Green color. You can click that.
This one. Screen record.
Yeah.
Down, sir.
Share screen.
Share screen. Okay, let me see where is that share screen. Somewhere here.
Are you able to see, sir?
Yes, I think I can now share my screen.
Yes. Yes, sir. It's visible now.
Yes, sir. It is visible.
Make it full screen, sir. Yes.
Is it visible, everyone?
Yes, yes. We can.
Yes,
see.
sir.
Yes, sir. It's visible.
Okay, excellent. So myself, Kamal Das, and as introduced, I have been working in IBM research for last 8 years or so. So before that, actually, I did my masters and PhD from IIT Kharagpur, mostly on mathematics and geoscience and related to computer science. Last few years, I think around 5 years or so, I have been working on agriculture related applications, which are actually dealing with how this future climate and the mitigations and resiliency plan for supply chain and agriculture domain. So today what I'm going to talk about is like how to estimate or map the soil nutrient at a different scale over space as well as the time, using data driven approach. So when we say data driven approach, it's come out it's nothing but the application of AI techniques or ML techniques, right? So these techniques require a lot of data, so that's why the last part we call it data fusion. So if you can think about in layman word, getting the data from different sources, and some of them are not in the same scale. Data harmonization is something we call here data fusion. So the talk talk will contain some of the introductions about how this future of climate things are happening, or what is actually the future of climate, and then why do we need to map the soil nutrient, right? And if we need to map the soil nutrient, how we can do that, right? That's another segment. And I'll briefly talk about three case studies, which me and my team have been done for over a few years. So basically, I organized them like case study one will be how ML model or machine learning model can be applied, or how to evaluate them. And then second model will be or case study will be based on our experience when you deploy the deep learning based model for mapping the soil nutrient. And the most recent and I think most matured work out of these three is the case study three, where actually we try to solve a real scenario where maybe a farmer or a client or a agriculture sector which provide fewer data points as a ground truth and ask for provide you a very fine scale or field scale soil nutrient map for their fertilizer applications or so, right? So case study 3 will I'll elaborate little more than the other two. So please stop me anywhere if you have any question. I can clarify on the way. Hope I am audible to everyone.
Yes, yes, you are audible, sir.
Okay. So let's come to what is future of climate and how they relates to agriculture, right? So if you see the you know I think everyone is very well informed or actually knowledgeable about the climate things. But if you see the recent hype about the climate, most of the big companies, even the universities are already there in this climate research domain. But now the big companies are also doing the similar thing, right? They're making a lot of noise about climate and climate change, right? But these things are there for a long time. And if you see the frequency of different natural hazards or extreme events are happening around the globe are actually rising. So their frequency is getting higher and higher. So they have a different impact in different domain. So health sector, there will be different impact, but I guess the future of climates, if you talk about them, then it has directly impacting the agriculture the most. So the reason being, uh, the agriculture productions are actually related to different factor of weather or climate, long-term climate impact, right? How the precipitation will be, how the that will directly impacting the crop yield. And maybe if someday some year you have a drought kind of scenario, the entire supply chain will be impacted based on that particular region. So entire globe is connected through this kind of extreme events which are happening around the globe due to the climate change scenario. So how to address that part is something we are actually working around for a long time now, more than 5 years or so. So then the water scarcity, inundations, and then there are other impact on ecological cycle of on the earth happening due to the climate change. So when you come for agriculture, right? So agriculture, we have a very bicycle feedback curve kind of. You actually agriculture do a lot of gas emissions. There are many fertilizers day by day. Farmer are using more and more fertilizer on their soil. And due to advanced crop management practices, it also kind of gives some direct feedback to the climate change scenario. So this climate change scenario impacting, like, there will be a uncertainty in pattern of rainfall or temperature rise, then pollutions, everything's are as a kind of summarized or coming from the climate change directions. Again, this is go to the agriculture, and then it will actually change a lot of other things, how the agriculture traditionally perform, right? So they have a kind of bi-directional feedback. So in this scenario, you have to be very, very accurate in applying your precision agriculture methodology, whether it is irrigations or is it fertilizations, or how you do the crop seasoning, right? So in traditional manner, when you come to a farmer, and especially they go, they grow crop in a particular seasons of the time, right? The crop seasons, which actually, if you see the temperature and the climate, precipitation pattern are shifting by each of this year. So essentially, these fixed term crop cycles will not remain the same as a fixed term crop cycle, right? So farmer need to adopt that kind of changes in their crop practicing. So today's talk is not about those part, how this climate is impacting those other things, but how this soil nutrient mapping over space and time is actually happening or can be done. And before that, why you need to this soil nutrient mapping first and place. So if you give if you think about this requirements, there are few pointer I noted here, like risk management and environmental management, your planning. So planning can be for agricultural production purpose, or planning for, let's say, a government is planning for something on some region. So there are so many dimension of planning, right? And risk assessment related to soil. You need to have the soil nutrient or soil health maps ready for that kind of scenario. And when you come for running a climate model or predicting the climate for future scale, seasonal scale, you also need the accurate spatial mapping or a continuous data for soil nutrient across the regions where you want to do the modeling or predictions, right? So that is another requirement. Now for precision agriculture, we need to have a very high spatial resolution soil nutrient map, especially for applying or actually fertilizer applications or plant productivity, right? And these are the few of these requirement for soil nutrient mapping. If you go beyond these bullet points, there will be ecological, environmental, directions where we also need soil nutrient map. So each of these requirements has a specific need or specific temporal and spatial frequency required for their application. So now how we can do that part? So conventionally or traditionally, there are IoT devices or ground sensor which actually sense the soil properties. And mostly recent times we see a lot of IoT devices. Some of them are paper based devices, mobile based devices which can sense the soil nutrient. But traditionally, if you go beyond this IoT devices, then there are a traditional approach like collecting sample from the soil, from the field, and pack them, and those samples go to the lab and do their testing and find out the different component of the soil or soil nutrients component. So that's the classical and more traditional approach to sense the soil nutrient. But this approach is not scalable, right? Because how many places you can collect sample and do the testing? And this is not a one time job, because the soil nutrient can also change over longer period of time, right? May not be in one season, but if you think about longer horizon of time, this data, this soil nutrient is not constant or static, right? So therefore, there are other scalable approach like remote sensing based approach. So there are essentially two types of remote satellite if we classify them on their sensor type. So optical sensor and the microwave sensor. So mostly, if you see the optical sensor, they scan the surface based on the multispectral properties of the surface, or you can think about as a RGB images, right? So their values will be different based on the characteristic it scan over the surface. Now this optical sensor will also have a lot of limitations when it comes, because these are the sensor which are affected by cloud weather conditions, this kind of scenario. And then there is other kind of satellite like microwave satellite, uh, which are all weather conditions case, or even it can scan through night. But this microwave satellite are mostly capture the structural property of the surface. So more first one is optical sensor can be, can be used as a proxy of getting the uh, soil nutrient characteristics across the surface, whereas microwave satellite can give you the structural information of the surface. So you're using both of these two with some sort of empirical relations, or using the ground sensing data to find out the relations, and can use as a another estimation method. Now then, the third, or C, which is we call here, I call it deterministic approach, but sometimes you can think about a combination of deterministic and statistical approach, like what we essentially do, like interpolation technique, right? If you have few data points over a space and you want to generate missing data points informations by doing some interpolation, so then there are essentially two kind of approach. One is non-geostatistical approach, which is like inverse distance weighting approach. So if you search through Google, there are various kind of this method are available, and even advanced uh, deterministic approach are also applied for soil nutrient mapping cases. Then there is another set of approach which is called geostatistical approach. So if most of us may be known about what is geostatistical approach, so this is a approach where actually we applied the pattern number of data points, or let's say ground truth data we have, and from those data points we find a semi-variogram curve or pattern, and then we fit some kind of functions, maybe linear, exponential, spherical, and then use that for mapping the you know or make the gridded data or continuous data over a region of study. So that is something called geostatistical approach. But today I'm going to talk about this approach. So my purpose of this talk is more about giving the probabilistic approach. So that is directly we can call it AI approach, or if we be very specific, then ML or DL approach, right? Here in this probabilistic approach, we need to actually we are using all of these three data sets above we mentioned, like ground truth data, remote sensing data, and then sometimes we also use the geostatistical or non-geostatistical approach. I see some chat. Maybe let me see what is that. Some question. Let me try to fix the background noise. Sorry about that. Actually, there was some noise. It's not bothering me, but of course, I think in other end it may be very noisy. Is it any better?
Yes, sir.
Yes,
Yes,
now
sir.
fine, sir. Now fine.
Now fine, sir. Now fine, sir.
Okay, thank you. So, I want to give more about how we can do the soil nutrient mapping using AI approach. So let me go to that part, and I'll start from the case study one. And before case study one, let me give you very informative and very uh, uh, kind of very informative to me, because when you go for AI techniques, we want to understand how this AI or a ML model framework would be, right? So I just try to create a generic framework so that we can get some sense how what could be the next 3 case studies based upon this framework. So first block about getting the data. So that is what is required for running ML model, right? So data we can classify as a target variables and the future or predictor variables, right? So when you say the target variables for soil nutrient mapping, we are talking about here is the ground truth data which are coming as a target variables, right? And then predictor can have different sources. So what I want to give in this presentations, mainly 4 sources. One is from satellite data. This satellite can be optical or microwave or combination of both. And then the climate variable. So if you think about soil nutrient as a uh, as a spatiotemporal variables, then it does have uh, kind of static values for one season. But if you consider that temporal horizon is longer, then it actually does have very good correlations with the climatic condition on that particular region. So climate variables another climate variables are another source for kind of understanding the soil nutrient dynamics. Then the third, the soil properties. So soil properties, what I meant to say, so if your soil is mostly dominated by, let's say, clay, sand, or silt, uh, so each of these components which are dominated by, they have a different characteristics on holding the soil nutrient other properties, like how the micro or macronutrients they contain, especially like soil nutrients, like sorry, soil like sandy soil, they actually the infiltration is very high in the soil, and therefore mostly we don't find much of, nutrient content in the soil types of sandy soil. So therefore this soil property is also another input, another informative input for modeling the soil nutrient dynamics. And then the third one is the topography. Of course, the elevations and topography of regions, they actually dictate how the accumulation of soil nutrients are going to happen on particular regions. So therefore, topography and the derived features from the topographies are very important for soil nutrient mapping cases. Now, these four set of data are not basically used in every case studies. Maybe some of them are using, but the case studies which I I want to elaborate more, the third case studies, there I want to give each of these data sets how they have used. Sorry, let me give 30-second break because this noise is coming again. Let me fix that. Sorry everyone, working from home makes life very difficult sometimes.
So it's okay, sir. Okay, sir. Please, sir.
Yeah, so then all this data and this framework is kind of generic. One can actually one can have many other sources which they think or they find very useful for making the model, so they can ingest all those other data sources from any of the sources or any other sources. So now this all this data will go into data processing framework or modulo. So in the data processing modulo, there will be multiple kind of steps. So one we need to do is, like, in the data harmonization part, every data should be in a uh, same spatial or temporal frequency, right? So let's talk about the spatial frequency. Like soil ground data is coming in a point source, like they are a point measurement. Remote satellite data, they do have some fixed pixel resolutions and some variable temporal frequency from single satellite. Climate variables depends on the source. They can have very coarse resolution as well. Soil property, same with soil property. Topography, we can get very high resolution data set, open source data set as well. So we need to aggregate all these data source into a uh, you know uh, a harmonized manner, so that it has, or sometimes we need to do some upscaling or downscaling to make this thing harmonized, right? And after that we need to do the feature selection. So when it comes to feature selections, this is seems to be simple, but sometimes it can be very complex. And here the domain knowledge, like someone is very someone is expert on soil science, they can help us, or they can do a lot of additional filtering how those features can be selected. Like, so I can call it like knowledge extraction or knowledge pattern extraction part. there the domain knowledge can be used apart from the statistical knowledge, right? And then each of these data set we can label and make one on final tabulated data set maybe, and then that can go for the next module, which is the model building exercise. So into the model building exercise, based on the model, like if it is a simple ML model, we can do the traditional splitting, or if we want to go for block diagrams, kind of splitting, like if you do have some temporal dimension in the data, then traditional splitting may not be giving a good result. So that is another part, how you can split the data to keep this data as a train and validations or testing part. And this can go for few iterations, right, before achieving the stable results. So once we get the stable results, so we can finalize that model, and that model can be deployed for mapping the soil nutrients, or for that regions wherever we want, right? So that is again coming from, we need to have, when we want to go want to deploy that model, we have to have the all the predictor variables across that regions in the required, or spatial scale, to do that part. So I see very important questions. How we figure which type of data to consider on priority when multiple types of data are available for tapping or mapping, maybe. Yeah. So this is very important question. Now in machine learning scenario, there is something called optimal data requirement for building the model. You can have similar or similar kind of characteristic data from multiple sources. And I guess if I understand correctly, you want to say that which which one to consider when you have the similar variables from multiple sources, right? So best, we can't say the which one to select, but there can be some approach you can consider before selecting them, like do the uh, collinearity study, whether those data sets are having very high correlation amongst each other. If so, then if you want to consider all of them, then your machine learning model need to be modified. Like those are not all the algorithms can consider this collinear data set very well, right? So you have to have consider a algorithm which can handle this kind of scenario. Now if you don't want to do selecting them, or you want to get out of all these three variables, a single variables which can impact the model most significantly, then there can be two approach. Number one, the one having very high correlations or relations, let's say correlation may not be the right measure, uh, with the target variables, you can consider that. Or if you say to me which one to consider, then what I will do, I'll do some sort of ensemble approach. Like out of all this, I don't want to lose any informations out of all these similar variables, so I'll do some kind of ensemble over all these data sets and make it single data set, and then I'll provide to the machine learning based model to use it as a feature data. Hope I have answered that question. Okay. uh, let's go to the case study part now. Please ping, ask me if you have any more further questions on the framework part, because this is the framework which will be used, mostly used by many of these special applications, not necessarily soil nutrient. If you want to do some other tasks, you can also follow this kind of framework and do your machine learning work. Or
I would like request participant. Do you have any queries, please? Now, time to ask queries regarding the framework. Sir, I think chat box they are raising some questions, sir. They posted.
Yes. Yes, I'm getting some question, KB Uma. So, shall we apply any of the feature selection technique? Um, yes, you can apply features. Now this question is very specific to the algorithm you want to apply. Let's say you are simply talking about uh, simple machine learning algorithm, let's say random forest or multilinear linear regressions, and how you do the feature selection there in that study, right? So you can do kind of simple ranking of those features based how they are actually relates with the target variables. That will be the most simplified way, but you can also go beyond that simple approach, right? But I think for a beginners, always best approach can be start with the how this variable important be variable important ranking, right, with the target variable. That will give you a most stable scenario, whether it is uh, you know coming from a different algorithms or random form based, and then you can think about the advanced approach, right? And even nowadays, nowadays there are actually different uh, libraries available which are actually helping you to make your machine learning process data processing part much easier. Like you throw bunch of data sets or feature vector, and they will figure it out, or they will kind derive secondary features uh, which are having much more impacting on the machine learning based model. So what I meant to say, you can think about a PCA, principal component analysis, right? It can help you to reduce the find out, to find out least number of variables out of large number of variables, right? The kind of similar approach, but those are like most sophisticated approach. What are the measure of what are the measure for multi-collinearity problem? uh Multi-collinearity problem, yes. You can rank those variables based on correlations with the target variables, or the correlations with themselves, and actually you can find out whether they are multi-collinear collinear or not. So simple approach could be, let's say I want to give a threshold value of correlations between themselves as a 0.8, and if anything above that, I say that they are collinear, and if they are below that, then you can say they are not collinear. So depending upon the problem setting and the variables you are talking about, we can define those multi-collinearity measures. What type of data can we get from satellite sources? Is that available globally? Okay, Priyanka, this is a very important question. So yes, there are satellite which are commercial, there are satellite which are open source. So you think about the optical satellite, open source satellite like Landsat, Sentinel. Landsat is from NASA. Those are open source data you can get. And then you can also get the Sentinel 2 from European Space Agency. Mostly after few hours of capturing them, very high resolutions, so 10 meters mostly. So these are the two sources which you can get up, open source data. Then there are various companies, they are scanning the surface on so high spatial resolution in temporal frequency. Those data sets you need to buy, right? And microwave data set like SAR, synthetic radar aperture, you can get from Sentinel-1 from again European Space Agency, and then you can get radars from Canadian Space Agency. So there are several sources. You can do that googling, or if you have the access of Google Earth Engine, right? That's another platform, very good platform, where you can get all this remote satellite data on your region of interest. Yes, these data sets what I mentioned are global data sets. And of course you can also get uh, from IBM Pairs platform. Pairs is another geospatial platform from IBM, similar to Google Earth Engines. There also you can request for remote satellite data on your region of interest, and you can get that process data. So if there is no more question, let me go to that case studies work. I hope there will be a lot more other questions will come. Thank you everyone. Let me go to the next slide. So case study one is actually soil nutrient predictions using remote sensing in West India. So in Maharashtra, we want to use that study area data to evaluate the different machine learning based model, how each of these machine learning based model perform, right? That's the aim of that study. So this study was actually done under internship program. So one of my student Gunrikat, she actually performed this study. Sorry. Let me talk about the study area and the data source. So the if you know that government is government of India, they did some sort of they're actually doing that soil health card. So they collect the samples from each of the farmer, and they do the laboratory test and find out the different micronutrients component of the soil, and they provided them a soil health card for for a specific seasons or the duration of the time, right? So we have actually processed that soil health card data for Maharashtra region. So specifically we consider two districts, Pune and Ahmedabad, sorry, Pune and Ahmedabad. These are the two districts. We you can see the these bubbles, right? Red and blue bubbles. They are actually the ground truth data from coming from the soil health card. So essentially, the soil health card data is not geotagged, and you have to do a lot of processings and taking supplementary data to make it a geotag data. So we did that part. I think 2018 that time. I don't know whether the current data does have the geotagging or not. So then based on this data, if you see, the red are actually used for training data, and the blue one is actually used for the validation or testing data. And this particular regions actually dominating crop is actually sorghum, pulse, millet, sugarcane, wheat, and cotton. And the data actually collected is the season from Rabi and in between the Rabi and Kharif. So generally March to June they have collected the samples and provided or did the testing for soil nutrient map, soil health card data. So this is the study area. And other data source like feature vector, what we have used is actually we selected the Landsat 8 data from NASA. And of course, you have to consider that since the samples are collected on somewhere in March to April timeframe, uh, we also need to collect the similar time frame remote satellite data, and those satellite needs to be very clear, because if you have a cloud interruptions or cloud masking, then your information is not captured very good properly by the satellite data. So you have to be very clear that whenever you take this Landsat data, those satellites should be 100% cloud free or maximum cloud free. And then the Sentinel-2, we also consider Sentinel-2 from Copernicus Hub in the similar time frame. And using these two satellites, we actually compute various indices, which are actually found out through some of the literature study, even though there are not much literature available in that time on soil nutrient mapping. So we found out that brightness index, saturation index, and there are a few other indices which are actually having some relations with the soil nutrient values in this the spatial scale. Of course, NDVI is another index, mostly used index. So we compute these indices based on this two satellite data, and other data, static data. You can think about how we can get those static data like elevations. We mentioned about topography, right? From the elevations, we use the Carto DM dataset, which is at 30-meter resolution from ISRO. From the elevation data set, we compute the slope. Slope will actually, can give some information how the flow will be, nutrient flow will be, right? Aspect is another derived features from elevation. Flow directions. These are the actually informations we derive from the elevation data set through DEM, digital elevation map or digital elevation model. And then the climatic data source, we use the precipitation data and the radiation data from world climate data set, which is at 1 kilometer spatial resolution. Soil texture data, sand, silt, clay, I mentioned that, right? Sand, silt, clay, they are actually obtained from the soil grid data source at 250-meter resolution. Please let me know if you have any question here on this slide on the data source part. And all these data sources are actually publicly available.
Sir,
Yes, I'm hearing.
sir, here you are mentioning some indexes, no parameters.
Yes, these are the indices we
Some
compute from this satellite. Yes.
So are they standard or these indexes, these formulas are framed related to the soil colors?
Yes, very good question. Thanks for asking this. So these indices are actually standard indices. These indices are not related to soil, but if you go through the literature, right, you can find if not less than more than 1,000 indices are derived from optical sensor, and these indices are used for different application, right? For example, NDVI is like normalized vegetation indices. It can tell you the health of the vegetation, right? You can apply that same indices for many applications like health monitorings or your pesticides pest and disease modeling purpose, or you can infer that as your crop biomass growth, or you can infer that as a whether the surface is bare soil or it is actually having some plantation on top of that, similar to other indices, right? Those are not specific to soil, but I found out that through some literature, some correlation studies, that these are the indices which have some they are carrying some positive information, or they are actually correlating nicely with the ground truth soil nutrient data. Am I answering your question?
Yes, sir. Yes, sir. I got it. Because we are working with some colored vegetables.
Mhm.
That's what I'm asking, sir. Okay, sir. I
Excellent.
got it.
Okay, thank you. So then the modeling part is, I already talked about that framework, right? So it like you get the data from different sources, you do the processing, nothing but the harmonization part, and making that process data to a tabulated format to try and build your model. And then model building or model training is like, how you split the data, and that data can be used for two purposes, like one is model training and another is evolution, right? So this exercise is showing these two part only, how this model evolution is done with the soil health card data from government of India. So there are actually several other methods, but I listed here 4 methods. The multiple linear regressions, mostly used, regression technique, random forest regressions, gradient boosting, and SVR. So these are the 4 approach, and we're showing this tabulated data on, kind of model training as well as the testing phases. And the component, soil nutrient component we want to model is like nitrogen, NPK, nitrogen, phosphorus, and potassium, and the organic carbon. So these are the 4 component of the soil nutrients we want to do that evolution study. And the evolution matrices or model performance matrices is selected is R square, RMSE, and the systematic SMAP. So that is another mean absolute percentage errors, and the symmetric mean absolute percentage error is called SMAP. Now, I see another question maybe. What is SVR? So SVM, you know, right? So it's just a regression technique. That's why you call it SVR. Sorry. Let me go to that R square values. Now, if you see the model validation work, right, the R square values are not actually great. You see the R square values, right, for MLR, random forest. So random forest is having the higher R square value, but rest of this models are not great. Even the random forest based regression techniques, the R square values we are expecting from our error measurement approaches, what we see in the machine learning community, anything less than 0.5 R square value is considered to be not that great. But in soil nutrient case, actually, if you see the some of the literatures, the R square value of 0.26 can be considered as a moderate model performance. The reason being, soil does have soil nutrient data from these two districts. They does have a lot of variability, in terms of their spatial scale. So those variability is not able to explain by the feature data we considered in the previous slides, right? That's why one of the reason we concluded that model performance is not that great on validations as well as in the model testing data set, right? Now there is another experiment, sub experiment in this data set. When you kind of divide the regions into number of similar characteristic regions, like based on the climatic variables, elevation data, we can do some sort of clustering, support vector regressions, right? Some sort of clustering and make it similar performing regions, and then individually apply those machine learning algorithm on that clusters. Then we found out that yes, our model is actually significantly improved on those clusters. But when you try to aggregate or make a global model on that bigger regions, then model performance what we are reporting here is somewhat moderate, not that great. So that is our observations. Any question here on model evolutions part? And once more, I want to kind of give some explanation.
You carry on, sir. Something it posted chat box, sir.
How we can tackle variations when we observe data about soil as their R square values are below par in terms of literature review. Yes, this is a very relevant questions given that the slides I'm explaining, right? So R square value actually explain the variability captured through your kind of the predictive variables, right? If I understood correctly, the machine learning part. Now, if that variability is not explained by your model is not great, then you can go back to your data, source data, right? And ask yourself whether you have captured all the relevant data to make this model, or the data sets are is not actually able to explain those variability, right? So these are the basic questions we need to carefully evaluate. Now if you feel that yes, your data sets are adequate to capture the or build the model, but again your R square value is not great, then you can further spend time on explainability part of your model. If it is a kind of a gray box, black box, depending upon what you can explain inside the model. Now let me skip that part. Let me come to the other part, like for this scenario, this case studies, we are considering a single model for two districts in Maharashtra, Pune and Ahmedabad, and that area, if I go back to the spatial area, let me see that So it is around, 1, 2, 3, 4. So around 400 kilometer by 400 kilometer approximately the study area. So if you think about that study area, this is a really big study area, and a single global model was not able to give a adequate R square value. So then our answer was how we can improve that R square value. Our answer was then subdivide this region. Subdivide these regions based on, the similarity of, let's say, climate variables, elevations, and other informations, and make some clusters. So this cluster size can be, by, let's say, 50 kilometer or 100 kilometer boxes, and then each of the similar cluster you can apply individually or independently model, build your model. Then we found out that yes, our R square value is improving. So these are the some of the techniques you can try out to make R square values better. Great. So thank you. Then let's say we try to, our first target was to get this soil health card, make the model, and evaluate the model, and but finally, final goal is to generate the spatial map, continuous spatial map in high resolutions for that entire study regions, right? That is what we did by deploying that final model, which is the random forest based model. And we can see that the high granular variations of nitrogen, phosphorus, potassium, or organic carbon. So if you see nitrogen, NPK, they are having some sort of intercorrelations among themselves, but the organic carbons are having, different spatial distributions, which are not actually matching with NPK. So summary, yes, we can compare to multiple linear regression model. Other models are performing better. The things are that the soil nutrients and the predictor variables are actually not in a linear relationship, right? They have a very non-linear relationship. So that's why which are the machine learning model can capture those non-linear dynamics well, that they have performed better. Obviously, the random forest is something we can think about to do this kind of job. Okay, if do not have any more question, then I want to go for the next case study, which is based on deep learning based approach. The doing the same soil nutrient mapping on the same data sets on the same regions. And for your information, I also give the link of this paper. So this paper is published already in IEEE International Geoscience for Remote Sensing Symposium. Every year this conference happen, and most of this remote sensing people are similar kind of people who actually apply remote sensing data on different domain. They meet and actually have this conference. So particularly I have been participating this conference for last 7-8 years or so, and I find this conference very informative because uh, starting from NASA, European Space Agency, ISRO, and all the good universities which are doing research around the remote sensing, they are actually participated, and it's a huge conference. If you want to understand this problem in further, you can go through this paper for more details. So let me come to the second case study, which is actually applying the deep learning based approach. So same study area, Pune, around Pune district, Maharashtra, two district, Ahmedabad and Pune. And why we apply deep learning based approach? So our machine learning based approach, we have seen that we get moderate kind of accuracy, and our predictor variables from climate, from soil, from satellite, they are actually not helping much. So what if we don't use those predictor variables, but derive the variables from the ground truth data itself, which is the soil health card data, right? So that is actually our aim, and map those micronutrient, nitrogen, potassium, phosphorus, and organic compound. Same study area, same durations of the data, same data, which I actually explained in the previous paper. Here, what we did, we actually derived two, kind of data sets from the ground truth data. So that I know we have explained very nicely as a theoretical paper in that conference paper. So that one is called NBRV, and another one is called NBD. So nearest neighbor data points, nearest distance, nearest distance, and the nearest neighborhood random variable value. These are the two variables we derive from the ground truth data. The scheme what we approach, we applied, we explained in the paper. So let me give you some high level idea of what we adopt. So you can think about a geostatistical approach, right? So in statistical approach, we take the feedback from for a given point from the neighboring point and compute the what we call a semi-diagram pattern, right? Or curve, or the functions, or construct the function. So here we don't go that way. We actually try to use the informations by looking into the heterogeneity and the similarity of these variables, this ground truth data, and we derive nearest neighborhood distance and the neighborhood random variable values. And these variables are kind of one-dimensional array. Then we finally converted to them as a two-dimensional array to perform the classical convolution operations on top of it. And those two matrix you can think about as a input goes into the CNN model. In fact, there are two architecture we provided, and let me tell you that these two architecture may not be the optimal architecture. There can be any other third an optical architecture which can even perform better than this architecture. And of course, finding the optimal value of each of these parameters, right? That is very tedious job in deep learning scenario. Who are working in the deep learning domain, they knows that finding optical parameter in a given scenario is a very tedious job. So I'm not we are not saying that these are the two architectures giving the best value, but of course these two architecture are giving some reasonable value, what we have observed, what I'm going to explain in the current slides. So again, we compared experiment 1 and experiment 2. That is actually I explained in the previous chart, the architecture of two diagrams. R square, RMSE, MEE, and systematic mean absolute percentage error. These are the four measurement matrices. R square value, we can greatly see that the values of R square values are improved in many fold, or compared with the machine learning approach, right? So that actually tells us that yes, we can improve without any predictor variables the accuracy of soil nutrient mapping through deep learning based approach, and that is reflected through all these measurement numbers like R square, RMSE, MEE, and means systematic mean absolute error. All these numbers are improved compared to the machine learning based approach. Now, whether we can use this approach for universally, then I'll summarize that part as well in the next slide. But you can see the spatial distributions of
Kindly coordinate with our expert.
is there any question for me?
Would like request participant. Do you have any queries? I think you just carry on. I think.
Okay.
Yes, sir. Yes, thank you.
Yeah. So the spatial maps of the soil nutrient across the same regions you see the lot of spatial variabilities captured through the deep learning based model. But if you notice that there are some patch where you don't actually see much variations of soil nutrients, which you have seen in the machine learning based approach, but not seeing based on this deep learning based approach. Let me tell you that why it is happening in the deep learning based. So deep learning based approach, here we actually derive the secondary variables like in nearest neighbor distance and neighbor random values, right? Those are actually we derive concept based on the similarity of those variables and their heterogeneity based on the ground truth data, right? So wherever you see the ground truth data have a kind of very negligible variations among their values in that particular region. So there we don't see much variation in the spatial variability part as well. So that is one of the observation when you apply the deep learning based approach. And then other characteristic of this approach is that uh, it is very tedious actually to find optimal architecture which can give you kind of a better soil nutrient mapping scenario or final model to where you can deploy the soil nutrient map generation purpose, right? So that part is very tedious to find. And if you want to do this deployment of this model or building this model for a larger regions, then it is not suitable. The reason being it actually computational very intensive, and sometimes getting one snapshot of the results you need to wait for several days, right? So that is another part. uh, and finding out the kind of optimized parameters from better performing model, that is another kind of difficulty, or getting this optimal setting of the parameter for deep learning based model. So these are the three drawback we actually noticed and reported in the paper. And in terms of advantage, of course, without any predictor you can do soil nutrient mapping. That is one advantage. Other advantage could be your accuracy numbers, right? What you see, what you have been seen, right? That increased based on the uh, with respect to the machine learning based approach. So let me take a pause here, and if you have any question, please ask it. Who are beneficiaries for soil nutrient measurement research? Where do we get, where do you get the demand of this kind of research? Thank you, sir. Yes. Okay, this is really important question on this talk. Why you actually need to have this soil nutrient mapping? Who actually care about soil nutrient mapping, right? I think this is the main question. Uh, so on agriculture domain, let me give you some example in the agriculture domain. So we are actually worked with several clients because we are in a corporate research domain, right? We are not doing a similar research as university people or professors are doing, right? They actually took a problem and try to solve this problem. If it is a novel enough, that will motivate them to solve, right? But in our corporate scenario or corporate setup, we can't do those kind of that kind of research. We have to solve a problem which are actually solve a real problem, as well as the same time that can be applied by some clients somewhere. So essentially when we try this problem to solve, then we focused where we can apply, and immediately after a year or so we actually got a deal with the client. And that deal is like one of the largest sugar producer company. They want to map their soil nutrient on their sugarcane farm. So they provided us few data points. So not like you can get uh, huge data points from those kind of client. So they actually did some soil sampling on their farm, and they want to use that sample data to map the soil nutrient across the sugarcane farm, so that they can apply the or they can do the management part of soil and fertilization based on the mapping. So there are various public sector or public companies, they are actually doing farm scale measurement of or collecting the ground truth data. Those may not be accessible to all of us, but if you are interested to get access of publicly available soil nutrient data sets collected all over the globes, then you can follow the soil grid data source. There you can get actually globally available soil nutrient data collected from the ground. Those are like measurement data, right? And this those data can be used for building model, deploying model for one region to other region by using transfer machine learning approach, there whatnot. These days there are so much research ongoing in the AI technique that even if your farm does not have any data, you can use those data and build a model, and you can kind of apply some transfer learning approach to deploy that model in your farm, or the farm of your interest, to actually evaluate your nutrient status. And these research are funded by various environmental sector people, multinational companies, uh, climate who are actually looking for the future of climate research direction. They also fund for this soil nutrient mapping scenario. Of course, in one of the example I just talked about, the client data, right? They share ground truth data, and our requirement to provide them a spatial map on their field, very high resolution. Yes, this is a very active research domain, and last few years I have been observing that this research is actually getting more focused, and the number of publications tells that story. Initially when you start, there are a couple of or few research paper we found out. Now you can search and you can find a lot of other research paper as well in different directions of soil nutrient mapping. Okay, then let me go to the last part of the case studies, which I want to explain a bit further. Is it okay? Can I take a 5 minutes break?
Yes, sir. Yes, sir. Please, sir.
Okay. Let me answer Shahid your question after coming from the break.
Okay, sir. So I would like to request all participants be stay on. Sir will be back in 5 minutes.
Somehow that recording is still there. Sorry for that. Okay. So there are 6 components of the soil nutrient they provided: electric conductivity, K, N, P, and organic matter, and the soil pH at 2 depth. One is in 5 centimeter, another one is the 30 centimeter depth. So when you do this kind of frequency count versus the range of values plotting, so histogram plot, you see that apart from pH, right, rest of them are actually has a very high dynamical variations, or by looking into their statistical variation like standard deviation, kurtosis, CV, skewness, they are actually very highly randomized. So in that scenario, what you can do, right? That is the difficult question to answer. So we tried our first approach is we tried is based on the deterministic approach, because you have very less number of data points. Your machine learning model may not be suitable, right? So what if we can do the job by deterministic approach, like Kriging or geostatistical approach, right? So then we found out the difficulty that uh, with this number of data points, even the deterministic approaches fail to get any sort of semi-variogram pattern. So once you don't get any semi-variogram pattern, you cannot apply your deterministic approach there, right? So this is the one of the drawback. Is it this question is to me? Share WhatsApp group link, sir.
No, sir. No, sir. That is for us, sir.
Now for us, sir, we will share, sir. We will share. I'm
Okay.
just sharing.
Yeah, and I think after this talk, I'll also share the slides. Is that okay?
Yes, sir. Fine, sir.
Okay.
Yes, sir.
Sure. So the deterministic approach failed, Kriging approach failed to give find out any semi-diagram pattern. So in that scenario, what we can do? We cannot apply simple the framework the simple machine learning based approach what we did previously for Maharashtra regions, because that the data points are very low and our initial assessment is that with that data set we cannot do much. So then actually comes the knowledge extraction part or domain expertise part. So we don't I'm not the soil scientist or I'm not the expert on soil science, but what we did actually, we try to find out the features which are most relevant and which can give more sense about you know building a machine learning based model which can be scalable and it can meet the accuracy performance and the spatial resolution performance criteria as well, right? So then we start with sentinel-2 data. Sentinel-2 data. Let me explain the sentinel-2 data. So we have we have plotted the sentinel-2 data by wavelength. So one is the wavelength in micrometers versus the reflectance values. You can see that as different wavelength and reflectance capture the different informations from the surface. Like so initially the lower the wavelengths actually capture the soil information most, and higher the wavelength it capture more the vegetation part, and so on, right? Now the first images actually is like RGB plot. So band 4, 3 and 2, red, green and blue. So when you do the RGB plot, it is like the human eyes, how we can see the image, right? So those three we can plot as RGB, and we can see that these images can tell us a lot of story. Like the greenery part maybe the vegetation field, and the gray part maybe the bare soil, and there are some other black areas which can be which may be the water bodies and some construction site maybe. So this is the area in Thailand, and we want to map the soil nutrient on these red boxes polygons. So these are like sugarcane farm. So first thing we notice that this data has a lot of background noises. The RGB plot itself telling us that it is not very clear, right? That these backgrounds are having some noises in the data. So then we applied one approach is kind of deriving the derivative of those bands with respect to the wavelength and to eliminate the background noise. So now whoever is expertise in the remote image processing part, image processing work, so they know that if your image has actually background noises, then those reduction of those noise can be done in multiple ways. So one of the mathematical ways is like you take the first derivative of that images with respect to their wavelength, and you can get another images which is the derivative images, and which does have some clarity or some less reduction or less noise in the background. What exactly is I'm plotting here? So first one is the RGB plot, and second one is the derivative of the RGB plot. And from your eyes, naked eyes, you can clearly see that the vegetation part is becoming more prominent in the derivative part, right? And the background of the soil is also more coming more prominently in the derivative part. right? Is there any question here on this mathematical work? How we can reduce the background noise of images? There can be multiple ways, but one of the simple ways to just to take the derivative of those spectral band or multispectral bands with respect to the wavelengths and make it more clarity, or we can reduce the background noises. So this is one technique we applied, and actually we get better features when you say about on the previous approach, where we actually use the remote sensing data and derive list of indices. So instead of going that directions, what we did is like we took a path, we plotted those RGB images, and we see that they have a background noises, and we just remove those background noises and make it more clear signal to get the soil informations from that derivative data. So that is one approach. And then of course we talked about digital elevation map model. So there, those digital elevation model, we derive slope, we derive slope, flow directions, aspect. And then from soil properties, earlier we only used sand, sand, silt and clay data from the soil grid data sources. But here in this model, actually we go beyond that. So we actually also brought bulk density, which actually have a good correlations with the with those macronutrient properties, and then soil organic carbon content, soil pH, and different depths. So we did that part. Additional variability were coming from the soil properties. And the climate, earlier our work was only consider the precipitation, precipitation and solar radiation. But here we also bring wind, because wind has some impact on the soil nutrient variability, temperature, and the vapor pressure. So these are the additional variable also we get from world climate sources. So you can get this data from these sources, like elevation data from SRTM 30-meter resolution, soil grid data from soil grid source at 250-meter resolution, world climate data set and 1 kilometer spatial resolution. Any questions so far?
No, sir. I think so. Some chart box. Sayed Nizamuddin already done it.
Yes, there are so many. There are some different smoothing technique or noise reduction technique in the image processing community, and derivative is one of them. Yes, derivation are not giving sometime accurate results. Yes, you are absolutely spot on. So yes, derivative always not give the promising results what you are looking for. Now in this example, we are getting some positive results, but that may not be generalizable. So ones need to apply different techniques, or based on their understanding, they can formulate specific technique to reduce the background noises. Here in this example, it is working nicely for by using the derivative part. Of course, if we don't find good results with first derivative, we can go beyond first derivative to second derivative, third derivative, or so on, right? What are the other best techniques we can use? I just mentioned there are a list of different smoothing technique. If you want to get very specific, maybe I'll share that some papers what I have read about them. I'm not specialist on that domain. Okay. So in the kind of modeling framework what I explained in the initially, right? So here we have feature data. We have feature data. I just want to number the feature data. So they're like sentinel data. We have a 12 bands, and now when you take the derivative of those bands, right? So sorry. So derivative of those 12 bands. So it's another 12 bands. And then what is the six? Yeah, soil properties. From the soil grid data, we have a six covariates or feature data: clay, sand, silt, soil pH, SOCC, BDSM. So these are like variables from the soil grid data sources. Digital elevation model will give us 4 data points like elevation, slope, aspect, and flow directions. And climate, they give 7 data, feature data. So in total, we have 41 feature data, right? And you have only, few data points. I think I mentioned 100 data points, ground truth data points. And so there is this challenge, right? How to build a model that is not actually overestimate or underestimate, or find an optimal model which can solve your purpose with this limited number of ground truth data. So we can build a kind of feature selection approach. Like your first, we start with soil pH. Soil pH is a function of, all these 41 variables. And then we try to do this cross validation approach, and we see that which or the optimal number of features can give you the best performing models. So out of these 41s, it seems that subset of 35 features, which is actually giving the RMSE values, optimal RMSE value and R square value, which is noted here in this table, right? Training phase and testing phase. There are different model. So I just noted here random forest version 1 and random forest version 2, based on these two scenario. And I think there are some questions. Let me see that. No question. So I just plotted one plot, the soil pH measurement data versus soil pH predicted data on trading and testing split. So trading data is on the red bubbles and testing data is in the the blue bubbles. And you can see in each of the split how the R values are. So more or less we are getting R value, which is correlation value, not the R square value, basically more than 0.8, right? So we can significantly, or we can definitely say that our model is doing a very good job, even we have less number of data points. And that same thing is also noticeable from R square value. RMSE value is also very nice, because if you think about pH value, right, they can vary from somewhere around 5 to somewhere around 9, right? And RMSE value is 0.5 is I think a very low number. Otherwise to say that model is very accurate. And another matrix we consider the Nash-Scuttley efficiency score. So NSE score. So on problem like handling the water resource or soil climate variables or soil nutrients. So any of such model, if you compute this efficiency score, if this efficiency score is above 0.9, we definitely say that the model is doing excellent job. And there are some threshold like 0.7 to 8 is, we can say that the model is doing a good job but can be better. And anything below 0.6 is not a good score. So in that point of view, in this model, pH model, it seems to be very good performing model. Now if you think about the soil nutrient, right, each of the soil nutrients are not independent, right? In some soil, if you have a higher nitrogen, it means that that soil will also have a higher phosphorus and potassium, because they are actually linearly correlated. And inversely proportional to soil NPK, the pH values go other way around, right? So if your soil organic matter is higher, then the pH value seems to be in the reversely proportional or inversely proportional. So using those kind of interrelations between the soil nutrient, what we did or what we followed here is like Next independent model we build is soil pH. And now when you go for any of this second Newton model, right, we'll use the soil Newton model or soil Newton ground truth data, their relations with that variable. So it is like starting with a independent base model from pH, and then subsequently the model will be like using their intercorrelations as well. Are everyone following me what I'm saying here? That
Yes,
way,
sir. Yes, sir.
yes, that way what we can do here is we can use their intercorrelations as another features which actually strongly influence this modeling performance of this, each of these individual component. So there is a very strong reasons why to start with pH, because we found out that pH is something which is mostly, there. If you go to the their descriptive statistics, only you can see that standard variation and skewness of pH is very stable compared to other of any of these variables, right? And of course total organic carbon can be derived from organic matter, so they are actually having some factor multiplied to each others to get other values. So we can skip the total organic carbon as out of the model. So we only target from last first six, and we start with pH, and then gradually we can select the other component which are having higher correlation with pH. So let me see, there are some questions or not. Yes, I think everyone is following. Great, excellent. I do have some other detailed slides somewhere. Let me bring that and give you some details idea, because this is going to help immensely on how do I minimize my screen. Escape. So yes. Give me a minute. I'm just try to get some detailed slides about this experiment
Yes, sir. Yes.
so that I can explain it a bit better. Yes. So this is the chart I want to bring here, give some ideas. So you can make a correlogram plot, like, correlations matrix plot, and you see the nitrogen versus the nitrogen component correlations with P, K, pH, EC, and organic matter. And you definitely can see that nitrogen has a very high correlation with organic matter. So organic matter, higher organic matter is higher nitrogen values. Similar with NPK, but when it comes for pH, it is negatively impacting, right? So you can just assess similar behavior with other variables and their intercorrelations. So that's why we build kind of how we can start building the model and their ordering. So we first with pH, and then once we finalize the pH model, then actually that model can generate the pH map, and that can be used for you know getting the second model is which is organic matter. So if you go to organic matter versus pH relations, you can see that there is some positive relations with organic matter versus pH, right? We can use that relation as well. So when you try to build the organic matter model, that will be function of pH plus all the covariates. Are you following my point? And then the next thing, when you try to build a model for potassiums, then your model will be function of pH, organic matter, plus all the covariates. Subsequently, you can follow similar step for other. So this is one of the optimal model we find, and based on your data set, you can find your own order. So for this data set, for this study reasons, we find this is one of the optical model to start. What should be your first model? pH is the first model, second will be the organic matter, and last will be the nitrogens. The reason being, in the data, the ground truth data, nitrogen has a lot of missing values, and it does have a lot of skewness, associated with it. And any nitrogens, if we start with nitrogens, our model accuracy drastically dropped. So that's why we actually kept nitrogen as the least, or the lowest, the last model to build, where we can use all the other feedbacks from different climate, soil nutrient sources. So these are the little information which actually help a lot on building a stable, accurate machine learning based model. So it is, you can think about machine learning based model as a gray box, where the other processing part and knowledge extraction part plays a very significant role to make a model very explainable or high accuracy, right? That's what I want to explain here. So I have not put all the other model and their accuracy, more or less. What you are seeing as a PAs, right? Similar accuracy followed in other soil nutrient model. Thank you, Shahid. This is actually, initially we did not perform those kind of intercorrelation study, but when when you try to face the real problem, right, less amount of data, you have to provide a high accuracy model, you have to look for different options or different scenarios. So there we actually found out that intercorrelations helps us a lot building those kind of models. So finally, let me summarize what I have done this case studies 3. So soil nutrients has negative correlations with multispectral band, strong with lower wavelength, reflected the higher wavelength. Yeah, that's part I already explained the derivative portions. First order derivative actually helps us a lot to actually improve the model performance. Climate variables, especially the wind conditions, vapor pressures, even though they seems to be not very promising, but when you go for building model and their intercorrelation analysis, right, we found out that those additional climate variables are actually immensely help to get better model accuracy and stability. Elevation data, simple elevation data may not be that helpful, but derived features like slope, aspect ratio, and flow directions, they actually help us a lot. And eventually you can find some pattern like inside how this pH value actually varies with the elevation data. Like higher the pH, lower the elevation. Maybe you can think about on top of a mountain you have lower pH, but whenever you come closer to the sea level you have a higher pH in the soil. So you can think about this way. Soil properties are essentially very important features. So they even though they are derived from model using remote satellite data, but at 250 meters spatial resolutions across the globe, they do actually have some positive impact on building such localized model at hyper resolution scale. So you can always, if you don't have any ground truth data, you can use soil grid data as a ground truth or as a proxy. But if you want to build a high accuracy model, you can always use soil grid data as a feature data to make your model perform better. There are some variability of each of this model due to their actually spatial pattern. And what methodology we propose in this slide, actually this actually accepted by the community as a one of the scalable approach to kind of generate a field scale or a very fine resolution soil nutrient map. And it has actually got a lot of appreciations from the community. So I think let me go to some plots as a spatial map on those farms which I showed earlier at two depth, 5 centimeter and 30 centimeter. You can see pH, organic carbon, and electric conductivity on this first chart, and they are actually having some variation along the depth, right? So as depth increasing, pH is also increased. However, when actually you have organic carbon as an organic compound as a concern, then mostly the organic compounds are lying mostly on the top of the soil. But if you go a little bit deeper, then other organic compound are actually lower, right? That is same with the electric conductivity and nitrogen, phosphorus, and potassium cases. So black dots are the sampling points or ground truth data points, and you can see the spatial map. These are the maps generated at 30-meter spatial resolutions for I think 2020 seasons of after the crop harvesting. So one thing to add here, when you try to generate the soil nutrient map for a regions, you make sure that your farm, the bare soil can be visible from the sky, because if you have a crop on top of it, then your remote sensing signals are capturing informations which are mixed by soil and crop, right? And your if your surface is bare soil, then the informations captured by satellite are actually coming all from the soil, right? that is that is one of the important uh, consideration you have to consider satellite data for building this kind of model. So let me answer some questions, then go for some resource discussion. Let me start. Okay. So I think Shahid, this is not an offside question. I think this is relevant question as well. What tools I use? So I can actually for research purpose doing some prototyping, I do use Python or R libraries. And once those prototype are actually stable and we are confident that these are working fine, just give me a second. There is another phone ringing somewhere. Sorry for that interruption. Yeah, so mostly R or Python, but yes, I would prefer any machine learning exercise to do in R. But if it comes for deep learning approach, then I'll prefer Python. Whether all nutrient combined analysis gives soil quality? Yes, soil health monitoring and getting the soil health index. If you want to combine all these components together and make one index, let's say you want to say that based on that index value, you want to say that how this soil quality is. I think those index can be defined based on the application point of view, right? One application maybe differ from other applications on index point of view, but yes, you can do that. Soil scientists are doing those kind of analysis. I think they
Sir, that is my question. Hello,
Yes, I'm hearing you.
sir. This is Ramesh. My question, like that K, all those things, they are individual nutrients, I suppose. The potassium, etc.
Right.
So when we do the combined analysis, then we will get the quality of the soil, or individually we have to check the soil quality.
Yes. So when you talk about fertilization, right? Let's say
Yeah.
you want to see, the nitrogen deficiency is there or not in your soil, right? You have to go for individual nitrogen only, right? Now,
Yeah.
let's say you also want to see the micronutrients in your soil, like boron, manganese, right? Then you have to go for individual model. Now, overall, the application point of view, like ecological study, whether your soil is rich of all the organic matters, or soil nutrients, soil health is good for particular application point of view, then what the soil scientists do, they derive a composite index, they derive an index which are actually a function of all these micro and macronutrients. So yes, it depends on the application point of view.
Okay, thank you, sir. Okay, thank you.
Yes, this is a last question, Shahid. We actually do very diverse set of work in our team, as a whole team in IBM research, not only from India but all over the globe. So we have 13 labs across the globe, and many of our colleagues are from different parts of the lab. We are actually working on try to solve different problems, like starting from climate model. So we generate climate predictions from seasonal, sub-seasonal to seasonal scale, like 2 weeks ahead, what could be your weather condition to, let's say, one total crop season, like 6 month to 9 month ahead, the climatic scenario. Those are like modeling part. Then sorry, then we also provide soil moisture as a soil moisture mapping across the globe, which actually give a lot of feedbacks for agriculture purpose, like irrigation purpose, or building hyper resolutions weather model. And if you ever about IBM research, we also have a platform called Pairs, where we provide all the remote satellite data across the globe. We provide our derived analytic solutions like soil nutrient, soil moisture, weather conditions from TWC, the weather company, which is also part of our IBM research. And under future of climate, actually we also provide the supply chain scenario for application like agriculture, right? If you want to if you are, let's say, you are a company of, you are a Nestle company, right? You want to purchase corn from India, and specifically you are looking for a corn in somewhere in Karnataka, right? So under this future of climate, one season ahead or beginning of the corn seasons, we actually try to predict what could be the next season corn, under change scenario, like what is the risk of having drought, what is the risk of having flood, or maybe a disease attack. And considering all those scenario, also getting the feedback from climate model, what could be the potential yield of that region. So this is like a larger region scale scenario. We provide that input to those companies, they can use for their planning purpose, right? Those kind of work we also do in the under future climate scenario. Yes, blockchain. What is the blockchain link over here? Please share that. Any other question? And I think most of this audience are very well informed, and they are actually interested to have a future work. If you are looking for any futuristic work in this area, Of course, our three of the case studies, what I talked, all of them are published work. You can go on this link and you get all this, full paper. And the soil grid data set I talked about, right? That is very informative. You can get soil properties, many soil properties from these sources across the globe at 250-meter resolutions. And specifically for Africa regions, you can also get 100-meter resolution. So this is, I consider to be very informative data source. And I think one of the earlier paper we saw is that this paper talked about the machine learning approach, how they can apply it on soil nutrient mapping at high resolution. So this paper also come with data as well as some, I think, code repo is also available. So once if you want to try out something, you can also look for this paper. Hopefully I manage the time well. I think 4 minutes are left.
Yes, sir. Nicely answered. I would like a request to participant. Do you have any queries? Now time to open for the queries. Any questions? Say Kamal Das are with us.
There are a lot of questions, I think.
Yes, sir. It's solved in chat box only, sir.
Hopefully I'm visible in the.
Yes, sir.
Yeah, visible, sir. It's camera also.
Camera also.
Actually, I stopped my camera. The reason being, I'm working from my village.
Village, okay.
Yeah, this network may be sometime crazy.
Yes, sir. So, sir, will give. So I would like request participant. Do you have any questions? Any query relating the topic?
Yeah, any oral feedback also you can share it.
Feedback also, please. Just give your feedback.
Sir.
Shall I? Okay, sir. Sir, shall I?
Thank you, everyone.
Sir, on behalf of IAPM, sir, myself, Dr. Kamal, really, how you just carried the session was very well and good, sir. Starting from how data source and how you worked about that framework and using some cases about how soiling, sensors, how you're, taken all cases with example of published, papers also have seen. That is very well. I think many people are also working on that, sir. I think they will communicate with you regarding for collaborative works. Since we from Indian Institute of Plantation Management further will have a great association with you, sir. We are happy to associate with you, sir. I think almost all the participants, I think enjoyed. I think they enriched knowledge regarding the session. Thank you, sir. Hopefully we'll have more collaborations and more association with you, sir. Ganesh, sir.
Thanks. Thanks a lot.
Thank you, sir. Kamal sir. I'll talk to you, sir, for the detail.
Yeah. Maybe I can drop now.
Yes, sir.
Thank you.
We have some small announcement for participant. So
yes, sir. So I think.
So we'll be sharing all the recorded video for today's session, morning and evening session. Maybe within half an hour, we'll share it in the WhatsApp group and all. So you go through the video if any doubt or anything. So as I mentioned, the 5th day, 25 multiple choice questions based on all the sessions. Maybe 2 to 3 questions will come from this Kamal sir session, and 1 or 2 questions will come from my session. So like this, each and every session, at least 3-4 questions will come. So please go through the video and accordingly we'll take it the final exam.
Sir, excuse me, sir.
Yes, sir.
Sir, I don't have the WhatsApp group link. Can you just
already shared, sir?
Already shared, sir. The link I have shared in the WhatsApp group. Please check it.
Please check it, sir. WhatsApp group.
Can you just please share it right now so that I'll copy and paste it in my.
Yeah. 1 minute. I think yes. Venugopaal sir have shared.
Yes, sir. I'm sharing, sir. One
more time he's sharing.
Yes, sir.
Sure.
Click that link and you can join, sir.
Yes, sir. Yes, sir.
Now I share, sir, please.
Yeah, thank you very much, sir. Thank you very much.
Okay.
Thank you, sir. Welcome, sir. And dear participant, tomorrow's session, I think our resource person is Ramji, sir. He's from Puzzle. I think we'll have a more interaction, more practical exposure, AI related using cases application for Puzzle company. Hope everybody please maintain the time. Please sharp by 10 a.m. We'll start the first session. First and second session going to be engaged by the Ramji sir tomorrow. Hope we'll have more depth knowledge regarding for AI cases relating Puzzle company. And now, of course, second maybe third and fourth session going to be engaged by the Srivastava regarding blockchain uses case applications. So shall we wind up, sir?
Okay, is there any other clarification?
Sir, any clarification regarding today's session? I would like request participant. Do you have any queries?
Okay, fine, sir.
Okay, sir. Thank you very much.
And we'll meet again at tomorrow at 10 o'clock.
10
Okay,
o'clock.
so we'll share all the YouTube link for morning session and the afternoon session before 4:30. We'll share it in the WhatsApp.
Thank you, sir. Thank you very much. Sir. Thank you all. Thank you.